Hello friends, so today we are going to discuss three questions, and these three questions will be from our electric potential. Okay, 1 second. Okay. So first question. It is given that the electrostatic self-energy of a thin spherical shell of radius r carrying a charge q uniformly distributed over its surface is given by. Okay, so for a thin spherical shell, the electrostatic energy is given to us. Two identical such spherical shells are placed exactly on top of each other so that they coincide, forming a single spherical shell of radius r with a total charge of 2q. Then the correct electrostatic energy of the resulting system is. Okay, so we are given that we are having two shells, okay, and they are placed top of each other. Okay, suppose this is our shell, which is the bottom, and the coinciding one is placed on the top of it, such that its radius is still r, but the charge becomes 2q. So we have to find out what will be its energy associated with this particular configuration. Okay. So we are given that for a thin spherical shell, the formula is given to us, which is having charge q. So we can say that our self energy of one shell and let us suppose that is given as u, then this u will be equal to our q square, and its formula is given to us, q square upon 8 pi epsilon naught times r. Okay. Now we are having two cells which are coinciding with each other. Okay. So now in the second case, we are given that we are having two coinciding shells. Okay. And the total energy which is associated with these two coinciding cells, let us call this as our ut, which we are supposed to find out. Okay. And we can divide this the energy associated with these two coinciding cells into three parts. First will be the self energy of shell number 1. Second will be self energy of cell number 2, and the third will be the interacting energy between the charges of shell number 1 and shell number 2. So there will be, we can say, we can divide this total energy into three subcomponents. So we can say the total two coinciding cell, we can write total energy has three parts. Okay. So our part number 1 will be equal to self energy of shell 1. Self energy of shell 1. Let us call this as a U1, which will be equal to over Q square 8 pi epsilon naught times R. And the second one will be the self energy of shell number 2. Self energy of shell 2. Let us call this a U2. Then this U2 will be also equal to a Q square 8 pi epsilon naught times R. And third part will be our interaction energy between the charges of two different shells. Interaction energy between charges of two shells. And we can call this as U12 or U21, one and same thing. U21, and that will be equal to our product of two charges and 4 pi epsilon naught times R. Okay. Therefore, total energy which is a U2, a UT, and that will be equal to our U1 plus U2 plus U12, or we can write this also as U21. It's one and the same thing. Now we simply substitute the values. So we get our UT, that is total energy, will be equal to our, this U1 and U2 are same, so we can just write it as twice Q square upon 8 pi epsilon times R plus, and the last part is our Q square 4 pi epsilon times R. Okay. So from here we get that our total energy associated with these two rings will be equal to, this comes as, this cancel by 4, so this will be 2 times this relationship, so it comes as a Q square 2 pi epsilon times R. So if you look closely, it seems like if you directly substitute value of Q as 2Q, we are going to get that total energy, but that is not the case. Okay, so we have to sort it out in a different way. Next question. It states that a cube of edge length B carries a uniform volume charge density rho. The charge density is 0 outside the cube. The electric potential is taken to be 0 at infinity. Let phi naught be the electric potential at the center of the cube and phi 1 be the electric potential at the corner of the cube. Then the ratio of phi naught to phi 1 is equal to. So we have to find out the ratio of the phi naught to phi 1, and such that phi naught is the electric potential at the center of the cube and phi 1 is at one of the corner of the cube. So we are going to start this with our the potential formula, and then we are going to move forward. Okay, it will be a little bit lengthy to solve it. Doesn't look like a shortcut for that, but the solution is quite intuitive. Okay, so you can easily just follow it. So we know that for a uniform charge density, for a uniform charge density rho, the potential at a point r at point r. So we can write its general formula, which is our phi of r will be equal to 1 upon 4 pi epsilon naught, and this is our integral, and integral will be with respect to the cube, because in this particular question we are discussing the cube, and that will be rho times derivative of the volume and our r minus r prime and modulus. So this is nothing but our Coulomb's law in the electrical form. Okay. Sorry, integral form, not in electrical form. Okay. And so we can, for this particular section of our integral, we can write this as rho L square. Okay. And length here, okay, so we can say that our rho dv prime on r minus r prime, this will be equal to our rho L square, okay, where this L is the length of the H. Length of H, and in this particular question it is represented as B. Okay. Therefore we can say that our for any point R inside the cube, of HB. HB, we can write that our flux at a point R for HB, this we can write it as a constant K, and this comes as rho B square upon epsilon naught. And this K is nothing but a dimensionless number, which we can, and it only depends upon the, you can say, shape of the cube. Okay. So this our K is our a dimensionless number, and it depends upon the shape of the cube. Shape of cube. And therefore we are going to define this constant K as our for phi naught as well as our for phi 1 also. So therefore we can write that our, okay, now we come to our the shape of the cube, and the shape of the cube is given to us that it is having a edge of B. So we can just approximate draw it. So we are given that one is flux is given as one of the vertex and other one is at the center. Okay. So for the center, let us call this location as R0, and for other one let us call this as R1. and r1 we are going to consider at our origin, and our r0, it is going to have a coordinate of our b by 2, b by 2 and b by 2. Okay. So you can say we have our a center, and for center we are representing it as r0, and that r0 is going to have a coordinate of our b by 2 as well as b by 2, and the other part is our with respect to our corner, and corner we are representing as our r1, which we are going to consider it as a part of the origin. And like I said, we are going to denote our phi naught and phi with respect to this constant, because this term will be related to both the fluxes, that is our phi. So we can say that our phi naught for a distance b, or we can write this as our phi at a distance r naught for the edge b. This we can write as our k naught rho b square upon epsilon naught. Similarly, we can write our phi 1b, which will be equal to our phi at r1 for the edge b, and this will be over k1 rho b square upon epsilon naught. Okay, this we can easily deduce from our this particular expression, and we simply going to divide these two terms. Therefore, from here we are going to get that our phi naught upon phi 1 will be equal to over k naught upon k1. So we are only interested in finding out this particular ratio. Okay. And for that we are going to consider a, we can say, scaling property with respect to our cube. So we can say our scaling property, a scaling law, and we are going to consider that another cube, but we are going to consider another cube, but its edge is a scaled version of our original edge, but the density is same. The density is given as rho and it is not going to change. So same definition of our flux we are going to use, that is our phi at a distance r, but now with respect to a scaled version will be equal to 1 upon 4 pi epsilon naught, a integral, and this comes as the same t prime and r minus r prime. Okay, and now this integral will be of our new cube. Okay. So this new cube with side as lambda b, and once again we can write with respect to a scaled version, we can say that our r prime is equal to our lambda times u, and from here we can also write that our derivative of volume will be equal to our lambda cube and d of vu, and our r minus r prime will be equal to r minus lambda times u. So once again we come to back to our original formula, that is our phi with respect to our scaled version will be equal to 1 upon 4 pi epsilon naught integral, and we substitute all the values. So this comes as a rho, this is our lambda cube du, and this is our lambda r minus lambda u, and we can just rewrite it we can take this lambda is common from the denominator. So this comes as 1 upon 4 pi epsilon naught. This is rho lambda cube, and this is our dv, and lambda r minus u. And this goes by the square. So we can write this will be equal to our lambda square 1 upon 4 pi epsilon naught integral rho of our derivative of volume r minus u. So it means our this particular integral or its solution is nothing but that we have already written here. Only difference is that it is consisting of, it is consisting of a different variable. That is the only difference. Rest is our same. Therefore, we can write that our phi of lambda r lambda b will be equal to lambda square phi of r b. So we found out the relationship between the scaled version of our cube and the original cube. Okay. And now we are going to use the scaled version with respect to the original also. Okay. So now apply this to the center, or we can say that for cube of edge B, we already have its center equation, that its center, which is our r naught, is given as our b by 2 and p by 2. But when we are going to a scaled version, okay, so we can say for cube of edge 2b, let us suppose our center is now at our r naught, capital R naught, then this will be equal to our b comma b comma b, which comes as 2 times r naught. Therefore, we can write that for our lambda is equal to 2, we can say with lambda is equal to 2, I can write the equation that is of phi naught 2b will be equal to phi r naught twice b, or which we can also use here. We already have the relationship. This becomes lambda naught. Lambda is our 2, so this comes as our 2 square phi of r naught times b. Therefore, this will be equal to over 4 times phi naught b. Therefore, we got the relationship between the scaled of our length also. Okay. And if you want to, for the better understanding of this, we can also draw a cube with a scaled version of 2. Okay. So this, let us suppose this is a larger cube whose edge is now 2b. So this is a larger cube, and now its center we have denoted as our r naught. So this is our R0, capital R0 rather, and it's, you can say, it is governed by the our edge as 2b. So it means this R0 is our, in this particular case, is our b comma b comma b, and so this, okay, so this is minus b plus b plus b and minus b. Okay, so these are the respective coordinates. So we can say the center of this big cube, center of the big cube is, sorry, this is our R, not R0, is at R, which is our 0 comma 0 comma 0. Okay, and we also know, like for the smaller cube which we have drawn here, the corner is having the same coordinate. Okay, so they are going to coincide with each other. And we also know the point 0 comma 0 comma 0 is a corner of every small cube. Okay, and this is clear from this picture also. So we have R and its coordinate is our 0 comma 0 comma 0. Okay, so it is having you can say our, from the front we can easily see that it is consisting of 4 cubes, 1 2 3 and 4, and all these cubes are having one of the, you can say, corner having a coordinate of 0 comma 0 comma 0. So it means the center of the big cube, which we have represented as capital R, is having a coordinate of 0 comma 0 comma 0, and the corner of every small cube is also having a coordinate of 0 comma 0 comma 0. So from here we can further write it as that the for the big cube, this capital R is a center, okay, but for smaller cube, this capital R is as a corner. Therefore we can say that this our R is behaving like a can be divided into two parts. Okay. First, it will be with respect to a big cube, and for this big cube, this capital R is a representation of the center. Okay. And for small cube, this capital R is the representation of the corner. And now we can easily relate the potential at the, you can say, at the big center. Okay. And big center is nothing but we are going to use for that as a superposition. So you can say the potential at the big center potential at the big center, and we are going to use for that superposition. So let us assume that we have a flux big at R, and which basically means the potential at for a big cube. So this is our potential at R, which is represented as 0 comma 0 comma 0 due to all 8 cubes. Okay. And then we are going to have for our small and r. Okay. And here we are representing it as a I because we have a number of small cubes. Okay. And this is nothing as potential at r due to ith small cube corner. And we know that our potential we can just is our superposition. Okay. Therefore, we can write the equation that our phi for big at r will be equal to the summation, and we have total as our 8 cubes, and this comes as because of our small I at r. And we can easily find out for any one small cube, and we can just add them algebraically. So we can say for one small cube, whether r is our 0, 0, 0 is one of its corner, therefore we can write that for edge b, because the small cube is having a edge over b, and we can write that relationship as our phi small for our ith cube r will be equal to phi 1 b. Okay. And this is true for all first cube, second cube, third cube, as well as eighth cube. So you can say for each value of I which varies from 1, 2, 3 up till 8. Therefore, we can write that our phi for our big r will be equal to over 8 times phi 1 b. Okay. So we got the relationship between our by the superposition principle. Okay. But we also know that our phi for our big at r is also equal to phi naught 2 times b, which we have already derived. Okay. So we can simply equate them. Therefore, from here we can write that a phi naught 2b is equal to over 8 phi 1 times b. And we also know that our can say but our phi naught 2 times b is equal to 4 times phi naught b. Okay. Therefore, we can write that our one second. Yeah, we already know this. So we can just equate them, and from here we get that our 4 times phi naught b is equal to 8 times phi 1 b. So now it's almost done. We've got the ratio that our phi naught upon phi 1 is equal to 2. Okay, that was our final requirement. So in this case, we used the scaled version of our cubes, and in general we use the scaled version with respect to our, you can say, the Gauss law also. Okay. And so okay, next question. So it states that consider two concentric shells with radii A and B with A greater than B and uniformly distributed charges Q and QB. Show that the potential on the shells are given by these two equations. And part B, show that if the shells are connected so that they are at the same potential phi, then the charge on the inner shell is. Okay. So in this case, we are given that we are having two shells. And okay, so we have to remember in this case, we are representing the potential as phi. Okay. So don't get confused that this, I think in the previous question, I called this phi as flux also. Okay, so that is wrong on my part. We are dealing this phi as our potential. Okay, so please remember this case for this particular question. And so we are given that we are having a, you can say, okay. So in this case, we are going to use a general formula, okay. And that general formula states that for a thin spherical shell of radius capital R and charge Q, and so we can write that at a distance, at any distance R from the center, the potential is given as phi. Our RQ, let me write in different way. So we can say this equal to over phi for a shell of radius R and having a charge Q at a distance R, and that is given as K Q upon 2R small r, and a function of R plus R minus a function of modulus R minus small r. So this is a relationship we have to remember. Okay, basically it means that we are having a shell whose radius is given as capital R and charge is given as capital Q. And we consider a point somewhere here, suppose, and that point is at a distance of R. Okay, obviously, you can just draw a circle with respect to it. Okay. And so we find out that the potential at this particular point, which we represented as phi of R. So this formula we have to remember. Okay, we can derive it also, but its derivation is quite complicated. So we have to remember this straightforward, that our, you can say, the potential at any distance R from the center. Okay, from this is our center and this is our shell, and at a distance R, which is given as K Q upon 2 multiplied by R times R, function of R plus R minus function of R minus R and its modulus. Okay, because it's a negative term, so this point R can be inside this shell also, so that's why we put a modulus part here. Okay. And so if this point is on the surface of the shell, okay, so we can just modify this formula. So we can say on its own surface, on its own surface, and in that case our r is equal to capital R. So obviously the second term will be coming equal to 0. So we can rewrite this as our potential because of the shell of radius r and charge q at a point capital R will be equal to k q upon, now this r will be replaced by capital R, so this becomes about 2r square, and it gets as a function of 2 times r. So we have to remember these two formulas. Now in this particular question we are given that we are having two shells, so we are going to use this equation, this formula for our purpose. So only thing is that it's a lengthy one, but the solution is quite easy. So we are given that we have two shells, okay, and these two shells, we have an outer one and the outer is having a radius a and charge as suppose QA, and then we are having an inner whose radius is given as B, and let us suppose the charge is our QB. Okay. And we are given that our A is greater than B, that is given in the question. And based on the question that is given to us, so we have two parts. Okay. So in part A, we are going to find out our potential on A at R is equal to A and potential at B at R is equal to B. Part B, when they are connected with each other. Okay, then we come to that part. So we are going to start with the part A, and part A we are given that our RA, so we come to our first of all for our outer shell. Okay. So potential on the outer shell, potential on the outer shell, and potential at the outer shell means our R is equal to our A. Okay. And so once again we are going to use the superposition. So we can say our superposition, we are going to have potential at A will be equal to potential at A because of A plus potential at A because of B. And so in the first case, so you can say for outer shell itself, that is our phi A of A. Okay. So you can say that our phi A of A, that is our self potential basically. Okay. And for that we can put our capital R is equal to A and our charge is equal to our QA. So we get this as a phi at A because of its own, we get this as K QA 2A square and function of 2A. And then we come to our second part. Second part is our potential at A due to B, and under this condition we have our capital R is our B and our charge is equal to our QB and this small r is equal to A. Okay. So we need to differentiate what is our capital R and what is our small r. Okay. capital R is the actual radius of the shell, and small r is the point where we are going to find out the potential, like we have drawn here. Okay. So r is the actual radius of the shell, and the small r is the distance of the point where we are going to find out the potential. So in the part A, this our, here I forgot to mention that our small r is equal to A, okay, because the radius of the shell is itself A, and the point where we are going to find out our potential is also equal to A. Whereas in part B, the radius of the shell is B, and the point where we are going to find out the potential is as our small a, that is our inside. Okay. Therefore, we can write that our potential at A due to B will be equal to our K QB upon 2 times AB, and this comes as function of our A plus B minus function of our A minus B. Now we simply add them in this particular equation. So we get our potential at A will be equal to our K QA upon 2A square function of our 2A plus K QB upon 2AB, and this comes as a function of A plus B minus function of our A minus B. Okay. Next, we are going to find out our this for our second, that is our outer one, sorry, not outer but inner one. B is our inner one. Okay, A was our outer one. So we can say potential on inner shell that is our R is equal to B, which is our potential is our phi B. Okay, so please remember once again, this phi in this particular question is the representation of our potential. It is not the representation of the flux. And because I think in the first question or second question, I sometimes call this phi as a flux. Please remember, this is not the flux, but this is the representation of our potential for these types of question, because in the question itself it is given as a potential. So once again, we are going to use the superposition. And this superposition states that the potential at B will be equal to the potential at B because of B, that is a self potential, plus potential at B because of A. Okay. Now, for the first part, that is our phi B to B, and in this case our radius is our B, our charge is our QB, and this small r is our B. Okay. Once again, this R, capital R, is the representation of the radius where of the shell which we have taken, and this small r is the representation where we are going to find out the potential. Okay. So for our this self potential means we are having a shell whose radius is given as B. So here this R is equal to B, and we have taken the point that is itself on the shell. So once again, this small r is also equal to B. Okay. So this is the major. So therefore we can say the potential at B because of B will be equal to K charge is our QB, and this becomes about 2B square, and this is a function of our twice b. Okay. Now we come to our outer part. Okay. So we have our potential at B due to A, and now in this case our radius is our A, okay, and Q is our QA, because we are going to find out the potential at B because of A, okay, and the point is B. So now in this case, this is our inner radius, inner shell, whose radius is given as B, and we have an outer shell whose radius is given as given as A. So in this case we are finding out the potential because of this outer on this inner one. Therefore this R is equal to over A, and this small r is equal to over B. And so we simply substitute them. We get this potential at B because of A will be equal to K QA upon AB, twice AB rather, and it comes a function of our A plus B minus function of our modulus A minus B. So please remember, we have to remember this formula, otherwise it will be a little bit difficult. Okay, so this entire discussion is based on this particular formula. Okay. And we are already given in the question that our A is greater than B. This is given to us. Therefore we can write that modulus of our A minus B will be nothing but our A minus B. Therefore we can write that our potential at B because of A will be equal to K QA, and this is twice A times B, and it becomes function of our A plus B minus function of our A minus B. Now we simply add them, okay, by the superposition. Therefore we can say that potential at B will be equal to over K, and this is our QB upon 2B square f of 2B plus K QA upon twice AB, and this becomes function of our A plus B minus function of our A minus B. Now in the part B, we are given that these shells are connected with each other. Okay. So we have our part B, shells are connected. Shells are connected. Okay. So it means they are at the same potential. Okay. So we can say shells are connected. So potential at A will be equal to potential at B. Let us suppose this is phi. And the question we are asked to find out our phi B, which will be same. It's not a big issue. So for the sake of convenience, okay, let us, you can say the difference, let us assume that our delta of F is represented as our A plus B minus function of our A minus B. Okay. Therefore we can write both the result from part A. We can say phi upon K will be equal to over QA upon 2A square function of our 2A plus QB upon 2AB and delta of F. Okay. And we can write this as our phi of K will be equal to our, from second solution, phi of B is equal to our 2B square function of our 2B plus QA upon 2B and this is our delta of f. And we need to only solve these two equations. These are basically nothing but two linear equations. Only the solution we have to, you can say, take little bit lengthy time to solve it. And for that we are going to insert few variables. We are going to assume that a is equal to our function of our 2a upon 2a square, and b is equal to delta f upon 2ab, and c is equal to function of our 2b upon 2b square. Okay, and that is going to solve our purpose. Therefore, we can rewrite these two equations as our phi upon k is equal to a times charge on A, b times charge on B, and second equation we can write this as phi upon k is equal to b times charge on A plus c times charge on B. So now we simply subtract them. And our left side will be giving us 0, and the right side will be giving us our a minus b times qa plus b minus times our qb. Therefore, from here we can say that our qa will be equal to our c minus b divided by a minus b times qb, and we are going to plug it in one of the equations, either this one or this one, okay, like a simultaneous linear equations. Therefore, we can say that our phi upon k is equal to, let me put in this equation, q of a times b q of b. So this comes as a times c minus b, a minus b, and this is our qb plus b times qb. And we can take qb as common from here. So this comes as charge on b. This will be a times c minus b, a minus b plus b. Okay. Therefore, from here we can write that our qb will be equal to our potential divided by k, and this will be 1 upon a, and this is our c minus b, a minus b, and plus b. Now we are once again going to substitute it into the back of the equation. Okay. And so we already know that our a we have taken as our function of our 2a upon 2a square, and b we have taken as delta of f upon 2ab, and c we have taken as function of our 2b, and this is our 2b square. So one by one we are going to find out all these variables, equations rather. So this is our a minus b, first part. So we are going to find out our a minus b, and this comes as our function of our 2a upon 2a square minus delta of f, and this is our 2ab. So we can just take common as our 2ab, and this will be coming as b upon a, function of our 2a minus delta of f. Then we need c minus b. So we get this our c minus b will be equal to function of our 2b square minus delta of f 2ab. Once again 1 upon 2ab as common, so this comes as our a upon b, function of our 2b minus delta of f. Now we find out the ratio. So we get this as c minus b upon a minus b. Okay, so we simply divide these two terms. Okay, so 1 upon 2ab, 1 upon 2ab is going to cancel out, and this comes as our b upon a, f of 2a minus delta of f, and this becomes a upon b, f of 2b minus delta of f. And we also know, because we are interested in the denominator, so we are interested in this denominator. Okay. Therefore we can write that our denominator is equal to over a c minus b, a minus b, and plus b. So we simply substitute all the values. Okay. And so we get this denominator will be equal to our 1 upon twice ab, and let me write it separately. So we get this as our 1 upon twice ab, and here we are having b function of our 2a minus a times delta f, and this comes as function of our 2a function of our 2b minus, and this is our delta f whole square. Now we substitute it back into equation of our QB. So we get that the charge QB will be equal to 5 upon K, and this will be whole divided by 1 upon twice AB, function of twice A, function of twice B, minus delta of F whole square, BF twice of A minus A delta F. And which can be written as our 5 upon K will be equal to, because this is entire term in the denominator, so we get this as a 2AB, and times B function of our 2A minus A delta of F, and denominator will be our function of 2A function of our 2B minus delta of F whole square. And we can keep as it is, but let us, as per the question, we get that the charge on B will be equal to twice B potential times K, and rest we can put as it is, substituting delta of F back. So we get this function of our 2A function of our 2B minus, we have delta of F, that is our F A plus B minus F A minus B and its whole square. And in the numerator we are going to get this as B function of our 2A minus, this is A times function of A plus B minus function of our A minus B. So this was our charge on B. So this was the only thing is that the you can say the solution is lengthy, but the entire solution is based on only one single equation, that is this one. So we state that for any spherical shell of radius r and charge q. Okay, so if you want to find out the potential at a distance r, okay, so basic figure we have already drawn for it. So this is a shell of radius r, and we are going to find out the potential at distance small r. So this is our this entire formula. So entire discussion is based on only this particular formula, and we have to remember it. There is no other option because the derivation is very complicated and lengthy as well. So we are not going to discuss the derivation part. Okay, so we are only interested in finding out this particular solution. Okay, so it was divided in two parts. So we found out what would be the potential at A, potential on B, and then we found out what is the charge on B, shell B. Okay. So only thing was the question is a little bit lengthy, but it is quite, you can say, simple to solve. It requires a little bit of effort, but we get the answer. So this completes all the, you can say, 3 questions for today. Thank you.